We're told in the first problem that we're supposed to represent results as ordered lists of length 4, so that's a big hint that we should be doing this as a fill-in-the-blank type argument and doing 4 steps where we pick a number for each of the 4 blanks. When we're in the first problem, since we're trying to list all possible results, we are looking to see that we're rolling a 6-sided die, and so the numbers that go in the blanks are any of the numbers from 1 to 6. So when we say pick a first number, in the first step we mean any number from 1 to 6. In the second step we mean any number from 1 to 6, any number from 1 to 6, and so on. So the total number of possibilities here is, according to the product rule, just 6 times 6 times 6 times 6, 6 ways for each of the 4 steps, which is 6 to the 4th. In the B, we ask how many of these do not involve getting a 1, and all that really means is that in each of these steps, the algorithm is the same, but now when we say pick a first number, we're not allowed to use the number 1, so we can use any of the numbers 2 through 6 here. We can use any of the numbers 2 through 6, 2 through 6, 2 through 6. So we have different choices for each of the 4 steps, but still the algorithm is the same. So now we'll have 5 choices for the first step, 5 choices for the second step, 5 choices for the third, and 5 for the 4th step, and that gives us 5 to the 4th total outcomes. And then in C, of the original results, how many involve getting 4 different numbers? Well, again, the algorithm itself is pretty much the same. We could add the language here in step 2 to say pick a different number for the second blank, and then pick a different number for the third blank. But if in each of these 4 blanks the only rule is that we can't use a number we picked before, then as we saw in class, this means there are 6 choices for the first step, 5 choices for the second step, because it can be any number except for the one you picked first, 4 numbers for the third step, and 3 numbers for the 4th step. This number is 30 times 12, which is 360. And if you wanted to use this on your calculator, this is P64. Sorry, we're starting with 6 objects and we're filling in 4 blanks, and the numbers fall with each choice. So I'll put that in parentheses as a computational tool, but obviously that wasn't computationally very difficult to just multiply the numbers together. In the second problem, we're forming originally a list of numbers where we have distinct digits, and so again, these are all 4-digit numbers, so we can imagine filling these in by filling the blanks. And the 4 steps are really the same as the 4 steps above. Pick a first number, pick a second number, and so on. We do want to add the language that the second number is different from the first, third number is different from the 2 we picked before, and so on. So once again, I just have to know how many ways there are to do each blank. Now, one thing that's slightly different here is that in the first blank, we only have 9 choices. There's only 9 ways to do step 1, because step 1 has to be a number starting with 1 going up to 9. However, the second number for step 2, we can use any of the digits 0 through 9, so that's 10 options, but the only one we're not allowed to use is the one we picked first. So there are 9 choices for the second blank as well, any of the digits 0 through 9 except for the one we used first. Similarly, for step 3, the third number can be any of the digits 0 through 9 except for the 2 that we already used, so there'll be 8 choices. And then similarly for step 4, there'll be 4 choices. So the answer here is 9 times 9 times 8 times 7. You can see that's not P anything, so this is why I was saying that going straight to the formula is not really productive. You want to really think about what numbers are being multiplied together to give you your answer. In step B, how many of these numbers use the digit 0 at least once? Well, this is an example of what we call the complementary problem. This is actually a difficult problem to count directly, but what we could do is take the total above this total and subtract the number that don't use 0 at all. So in other words, take all of the ones that you could ever get and then throw out the ones that don't have a 0 in them. All the ones that remain will be ones that use the digit 0 at least once. The key word here is this at least once. When you see that, then there's a good chance that this idea of a complementary problem, that is, of counting a total and subtracting the ones that are not being described, will actually be productive. The reason that this number in parentheses here is easy to count is because it's exactly like part B up here. Right? Up here we counted the number that didn't have a 1 available. Same idea to count the number that doesn't have a 0 available. So this number, I'll count this. Again, I just use my same 4 steps. I'm not really ever varying the 4 steps. The only difference is, what options do I have for each step? Well, if you're not allowed to use 0, that doesn't affect the first step. Remember, we weren't possibly picking 0 in the first step anyway. So there are still 9 choices for the first step, any of the numbers from 1 to 9. However, now, in the second step, we have to use a number from 1 to 9. We're not allowed to use 0, and it can't be the same one we used before. So there are 8 choices for the second blank. The third blank, we're allowed to use any number from 1 to 9 except for the 2 we've already used. So there's 7 options. And similarly, there are 6 options for the fourth blank. And so the answer then is going to be the answer from above, the 9 times 9 times 8 times 7. That's the total number of numbers we could have in this set with distinct digits. And we're going to subtract the number, and I'm running out of room. Subtracting the number that don't use a 0 at all. So this difference is going to be the number that uses 0 at least once. And then finally, how many of the numbers counted in part A are odd? So we're ignoring B now. We're going back to part A. To be odd is a restriction on the fourth blank. And so that means that we need to, remember we said we wanted to organize our steps. Oops. We want to organize our steps from the most restricted case to the least restricted case. So if you tell me that the number has to be odd, if you tell me the number has to be odd, then that means that I need an algorithm where I first, in step 1, pick or I guess I should say, yeah. I'm going to pick the fourth digit first. In other words, I could call that the ones place or the units place digit. I'm going to pick that first. The second most restricted digit is the first digit, because it still has the restriction that it can't be 0. It still has to be 1 through 9. And then steps 3 and 4 are just to fill in the other 2 blanks. So I could fill in the second blank and the third blank. The order of those doesn't matter because they have no, one's not more or less restricted than the other. So if I follow the algorithm of picking this blank first, because it has to be an odd number, that has the most restriction, then pick this blank because it can't be a 0, that's the second most restricted, and then the other 2 have no particular restrictions. If I pick in that order, then I have 5 choices for the first blank that I choose, or sorry, for the first step. So 5 choices for this step. I've now used an odd number, so I can't use that number again, and I can use anything else from 1 to 9. So that's 8 choices for the leftmost blank. Now I've used 2 numbers, and in step 3 I can use anything from 0 to 9 except for the 2 I've already picked. So there's 8 choices for that. And then in step 4 I can use any of the numbers from 0 to 9 except for the 3 that I've already picked, and so there's 7 choices for that. So there are 5 times 8 times 8 times 7 ways that you're going to get an odd number out of the list above. And the third problem, we are once again electing officers of a club, and so we saw in class that we could do this by filling in the blank. We have 4 positions, so we're going to fill in 4 blanks. I'll say president, vice president, secretary, treasurer. That's how I'll represent the election outcomes. And so the total number of results possible is just the number of ways to fill in each of the 4 blanks. So I'll just say fill in left to right instead of writing out the 4 steps. So if I fill in left to right, then I have, how many do I have altogether here? Looks like I have 30 people altogether. So I have 30 choices for the president blank, 29 for the vice president blank, 28 for the secretary blank, and 27 for the treasurer blank. So the product of 30 times 29 times 28 times 27 is the total number of election results. And how many of the results is exactly one of the officers a math major? Well, it depends on which officer is a math major. So we could just break this into cases. It's actually a fairly easy thing to do in cases. We could first figure out what happens when the president is a math major and count those. Secondly, we could figure out when the vice president is a math major and count those. When the secretary is a math major, and when the treasurer is a math major. So if we count each of those separately, it will fall into the same kind of algorithm we had before. The only difference is whichever one is the math major, I should fill that blank first. So if I do that, where the first blank, the first choice is wherever the math major is, then, for example, when the president's a math major, there are now 10 choices for president, and it says only one, exactly one of the officers is a math major. So that means that all three other officers have to come from the other 20 members. So that means there are 20 choices for vice president, 19 choices for secretary, and 18 choices for treasurer. So just filling the numbers then left to right, where I insist that the first person is a math major and everybody else comes from the non-math majors, I would have something like that. The key here is that in each one of these cases, as long as you just do that officer first, so fill in the vice president blank first with a math major and then fill in the other 3, or fill in the first blank, the secretary blank with a math major and then do the other 3, what's going to happen is that the numerical answer for each of those is going to be exactly the same thing. All of them are going to have this same numerical value because you're going to have 10 choices for wherever you put the math major, and then 20 times 19 times 18 is going to be the number of ways to fill in the other 3 blanks. So in this case, there are 4 cases, but really the 4 cases are all solved in a very similar way, and they all have exactly the same numerical answer. So we're really just adding that same number to itself 4 times. In the last problem, there's really no good way to do this using a simple algorithm, so we really have to break this into cases. The number of cases can be pretty high depending on how you represent them, but each one is very simple to do based on our basic algorithm. So I would encourage you to read the solutions to this one. I'm not going to try to fit it all on the bottom margin here. You'll see what I mean when you see the solution. But basically, the big cases are. The big cases are. Depends on, you've got 3 majors for 4 officers, so you could either have 2 math majors, 1 computer science, and 1 education, or you could have 2 computer science, 1 math, and 1 education, or you could have 2 education, 1 math, and 1 computer science. So those are the 3 main cases, and we'll add up those results. But to count each one of those, you may have to consider other cases. So anyway, have a look at the solutions to those, and then I'll post the solutions to the back side of the worksheet on a separate video.